This video is for Math 0242-1342, review number 1, which covers chapters 1 through 3. The review assignment's right here, right after the 0242 homework number 2. And then the test, I don't know if you're able to see it. Sometimes they don't appear until they open. So maybe you don't even see test 1 here, but on October 6th, it'll show definitely by then, and maybe you see it now too, but it just won't let you open it till October 6th. So 0242-1342 review 1, there is 30 questions here. A lot of the early ones are kind of short answers. So a college faculty consists of 400 men, 250 women. The college administration wants to draw a sample of 65 members to ask their opinion about a new parking fee. They draw a simple random sample of 40 men and another simple random sample of 25 women. So once people hear that there's randomness going on in the problem, they think the answer is random, but it can't be random if you know ahead of time what's going to happen. If I know I'm going to get 40 men and 25 women, that can't be random no matter what. What's happening here is there's groups. We're dividing them up by gender, men and women. Anytime there's groups involved, it's either stratified or cluster. And then clusters when you take all from one or more of the groups, and then stratified is when you take some from each group. We're doing some from each group. There's 40 men and 25 women. Both groups are having some people take them. This is a stratified sample. A football coach randomly selected the varsity or junior varsity team and asked all players. See, there's groups, varsity and junior varsity, that's like male and female, but he's asking all players from one team only. That's a cluster sample. Cluster and stratified are very similar. One of them you're doing some from each, and the other one you're doing all from some. They're really backwards versions of each other. A manager at a family amusement park uses a random number generator to draw a sample based on admission ticket number to ask for feedback on new rides. So this is one of the truly random methods. You either put people's name in a hat and draw them out one at a time, or you give somebody some unique number like an admission ticket number, and then you could have our number generator spit numbers out in a range, and then you never know which one's going to come up, and each one has an equal chance of coming up. And there's no groups here. It says nothing about like adults and children or males and females or anything like that. So this is a truly random sample. Simple random sample. Okay, nominal or ordinal. This is when there's no math involved. I can't do averaging like blue plus red divided by 2 doesn't mean anything. So that's nominal or ordinal anytime that happens. And then nominal is just simply naming, labeling, categorizing, and ordinal takes it one step further, and there's a specific order to it. But blue, red, black, green, those are just categories. There's no order to that, so this is nominal. Discrete or continuous is a different system here. If you have qualitative or quantitative data, which is more generic than nominal, ordinal, interval, and ratio, if you decide that it's qualitative, you're done right away. That's similar to nominal and ordinal. But if it's quantitative, then it can be either discrete or continuous, and that depends if you count or measure it. Discrete are things that you count, continuous are things that you measure. And if it's hard to tell, what I do is, like if it's number of students in a classroom, not only do you count that, but it could be 30 or it could be 31, but it's completely impossible to be 30.8. So what I do is I think of 2 possible examples really close together, and could I get more accurate if I wanted to? That's completely impossible. It's either 30 or 31, nothing in between is possible. With temperature in a pottery kiln, it could be 300 degrees, it could be 301, but it could be 300.8 if I get a more accurate measuring device. So it doesn't have to be exactly to the nearest degree, and only integer degrees and nothing in between. And temperature is something that you measure, so that's continuous. A student's GPA, we want to know what kind of level of measurement that is, interval or ratio. So you have the nominal and the ordinal first when there's no math going on, but then once there's math, calculating somebody's GPA literally is an average, and if you can do averaging, that's mathematical. So anytime math's involved, it's either interval or ratio. Ratio is when there's a true zero level and you can't go into the negatives. So if somebody failed every class, now one thing I'm wondering is this GPA for high school or for college? It doesn't really say. High schools will often do it on a 100-point scale, and colleges do a 4-point scale. So somebody could have a 4.0 GPA in college and they would have straight A's. And then somebody could fail every class and literally their GPA would be 0. If you got all F's, you get 0 for your GPA. If you're a straight C student, you would have a 2.0 GPA. So a student with a 2.0 GPA versus somebody who's got straight A's and 4.0, the 4.0 is twice as high as the 2.0 because you're comparing from 0. If the values can go into the negatives, like temperatures go into negatives, so if this was about temperature, it would definitely be interval. Another example of interval is the human calendar system we made with the BC years are like negatives. So if it goes into the negatives, it's definitely interval. It sometimes, even if it doesn't go into the negatives, it can be interval if 0 is not the smallest possible value. And there was one that I didn't know one time, but there was one that said SAT scores. And I assumed, okay, what if you get every answer wrong? Do you get a 0 on the SAT? Like any other test, if you miss every question, you get a 0. But I thought it was ratio because I thought, okay, it must start at 0 and go up, and 1,000 on the SAT is twice as good as a 500. But apparently the smallest value is some positive number like 50. Because they said it was interval, and the only way it's interval is if there's not a true 0. So I think this GPA, sometimes it's hard to know unless you're an expert in the area. I think if you fail every class, you would have a 0 GPA, and it certainly can't be negative. And then if that is true, then somebody with a 4.0 is twice as good as somebody with a 2.0, and that would make it ratio if that's the case. Okay, they're saying it's interval. So maybe this is high school. You know, in high school, sometimes like the minimum grade, somebody might get a 50, even if they fail the class. So maybe they don't give them a 0. So what it comes down to, as I said, is if 0 is the lowest level, and you can't be negative, and the lowest level is not some positive number, then it's ratio. But apparently, because they're saying this is interval, it must be that this either, it definitely doesn't go in the negatives. Whatever GPA they're talking about here, it must not have 0 as the lowest level. Otherwise, it would definitely be ratio. So let me just try another one. That was maybe a bad example. The year of the next presidential election. See, this is interval for sure. I just mentioned that. Because 2028, 2024, 2020, if you keep going back in time, the calendar system we have doesn't have a year 0. Humans don't know when time started. So somebody just arbitrarily drew a line at one point and said, this is year 1, the next year is year 2, then year 3, and every year before that was 1 BC and 2 BC and 3 BC. Those are like negatives. So this one's definitely interval. If I try another one, temperatures go into the negatives. Celsius, you can have negative Celsius. So apparently number 6 is always interval no matter how many times you try it, but I wasn't sure about the GPAs, so that is just something that I guess you need to know a little more detail than what they said here. In a certain supermarket, 50 customers who used a self-service checkout lane averaged 5.2 minutes of checkout time, while 62 customers used the cashier, averaged 6.1 minutes. Okay, so this could be some kind of an experiment or observational study. And it seems like if you go to the self-service, you get out of there faster. 5.2 minutes versus 6.1 might be a significant difference, especially like in the long run for all the customers that show up every day. So the self-service checkout line, you just go faster, and then if you have to wait on the cashier, that can take longer, apparently just based on this. But we cannot say that the self-service causes faster checkouts unless we have a true experiment here. And that would take randomizing which lane people go into. And you really can't do that with humans. You can't say, oh, sorry, you got to go stand in this line because I randomly drew you to be in this line. Customers would get angry and just leave. So you have to let these people choose their own lanes. And this would definitely be an observational study because you couldn't force this on them randomly. And therefore, you can't say cause and effect. You might notice a difference, but it doesn't mean it was caused by the different lanes. So the treatments are the two lanes, the cashier lane and the self-service lane. Which lane you get in is the treatment. And that's why it says check all that apply, because there's really two groups. What outcome is being measured? It's how fast you go through that. So the time, the checkout time. I'm trying to measure time, how fast they get out of there. This is definitely an observational study because I cannot randomly place them into which line they have to go into. Customers would get angry. And go to any grocery store, nobody tells you what line to get in. You just go to whatever one you want. You can wait in a long line if you want to. True or false, the number of items purchased is a potential confounder. Definitely. A confounding variable is some other variable that might play a role in what you're measuring, even though you didn't want that to play a role. I just want to know, is putting it in myself versus somebody else doing it for me, does that make me get through faster or slower? But yeah, the self-checkout lines generally are people that have less items. People with giant baskets full of stuff, they usually go to the cashier where they let the other person do it for them because there's just so much stuff. So this is definitely why you can't say cause and effect, because it could just be the people in the self-checkout line on average have less items, and that's why they get through faster. Can we conclude it is faster? No, we can't conclude that, because you can only conclude that if you know there's cause and effect. Only an experiment can show cause and effect. Anytime you have an observational study, you can't make a definitive conclusion like that. Even though it seemed good. 5.2 versus 6.1. Okay, CrossFit is a relatively new strength and conditioning program. A fitness instructor would like to know if CrossFit is better for strength and conditioning than traditional programs. So it just comes down to, could I randomly place people in CrossFit or the old method? Is there anything dangerous, unethical, time-consuming, just not properly done? Like the grocery store, nobody forces you to go into a certain line you don't like. But if I want to be able to say that CrossFit is better and causes you to have better strength and conditioning, I have to get a group of people and randomly place some in CrossFit and the rest in the traditional method, even if they don't want to be in the group they end up in. So you see how it says, do you think it's possible to do a randomized experiment? Is it possible? Is there going to be any issue with me doing that? And maybe I don't know what CrossFit is, that so extreme fitness that maybe that would be unethical to put somebody in there that's not in good shape. Is that some kind of like military training, or is it if CrossFit is an extreme exercise and the traditional programs are more lighter, then I wouldn't do an experiment here, because that could harm somebody. But if it's like CrossFit versus a spinning class and they're both very, very hard to do unless you're in good shape, then you could do an experiment. So this, in my opinion, isn't the greatest example to be able to tell the difference. Because they're comparing it to traditional programs. It's just some new fad, in other words. So I would say that you could do an experiment here, because I don't think that CrossFit is greatly more than some other fitness program. All fitness programs are hard to do. If you're out of shape, any program is going to be difficult for you. And I don't know enough about CrossFit to know if this is an extreme exercise much more than any other thing you do, like go into a yoga class or a spinning class or a swimming class. So with my little knowledge about CrossFit, I would guess experiment. Maybe I'm wrong. Oh, no, okay. So yeah, so see, sometimes if you don't know, like that other one, I didn't know about the GPA, which one they were talking about. Here, I wasn't sure about CrossFit. Maybe you know more about it than I do, but sometimes you just get a bad example and you can try another one. A psychologist would like to know if students who take a psychology of gender course are more sensitive to gender issues after the course is over. So, is this an essential course you have to have? Or is it an elective? That can play a role here too. So, if this is an essential course you have to have, and you're either placed in this or you're placed in something else, that could harm you. Then I'm missing out on a class I have to have, and I'm wasting my time and my money taking some class that you're randomly placing me in. Then you would definitely want to do an observational study. If it's not an essential course and it's just a matter of picking electives and everybody has to have one elective and maybe you get one you don't like, but it's not an essential course, then you could do an experiment. So again, some of these, it would help if they gave us a little more information than a short sentence. Are you talking about only psychology students, or are these students in general? Is this is this a required class for psychology students, or is it an elective that just general students might be taking? That could play a role in this, in my opinion. Now, one thing too is the last time it was experiments, so sometimes when you do a problem more than once, it's always the same answer sometimes. But this could be an experiment as long as this is not a required course that absolutely you have to have. That would be an issue for, okay, so that's exactly what my point was, is that maybe they're talking about these are psychology students. It would have been nice if they'd have mentioned that. These are psychology students and they have to take this course. And if they get randomly placed in another course, then maybe they have to take more time and more money taking a course they don't need, and then they got to go back and take the one they do need. Okay, at least this answer isn't always the same. So if you do it more than once, this one's actually beneficial. A scientist wants to determine whether people who live in places with high levels of air pollution get more colds than people with little air pollution. Now, this is a very fair question right here. This one is very clear that I could definitely not do this randomly. It would be very unethical to randomly place people in high air pollution areas just for your experiment. You would have to do an observational study here. And if people choose to live in areas that have a whole bunch of pollution, that's on them. They chose that themselves. So this is definitely an observational study. It would be unethical and harmful to people to randomly place people in a place they don't want to live. And that's a clear case of an observational study right there. So some of these are just better than others, and sometimes it's the luck of the draw, unfortunately. In an experiment, half of the participants are randomly assigned to sleep on a new type of mattress, while the other half sleep on the standard mattress. And it did say they were randomly assigned to this. So then it could be an experiment. The next night they sleep on the other mattress, okay? So each person's getting both mattresses. And this is only 2 nights in their whole life. So, and you could definitely get people who volunteer to do this too. Then you could do a true experiment on a case like this. Now, I've seen one like this before where it was like, buy a new mattress and you get the cheap one or the luxury one, and then you get to have this for the next 8 years of your life. Then you have to do an observational study, because if somebody randomly gets the bad mattress and then now their sleep is ruined, it could greatly affect their life going forward. Their job, their work would be, their family life could be all affected just because of a mattress for your experiment. Although this isn't even about if it's an observational study or an experiment. Okay, so the result is likely due to confounding or likely not due to confounding. Okay, so confounding is there any other variable besides the type of mattress that might be playing a role here? In an experiment, half of the participants are randomly assigned to sleep on a new mattress. The other half get a standard one. The next night they sleep on they just switch mattresses for a second night. And each person's asked which one made them feel more rested. So there does not seem to be any confounding here, because this is such a short thing and everybody's getting both mattresses, so it's not even unfair just the order of the 2 nights. And there doesn't seem to be anything else. It doesn't mention anything like some of the people are old and some of them are young, and so maybe just that's another variable that's playing a role, or some people have good health, some people have bad health. Things like that could be confounding variables, but you usually don't want to assume they're happening unless you see them in the problem somewhere. So I would say there's nothing that they told me here that sounds like it could confound the results and be some other, like the shopping example where people that go to the self-checkout line are very likely to have less items than people who don't. That was a pretty obvious one, but this one, it didn't seem like any other variable was going on besides the type of mattresses. Blank are highly unreliable in part because people have strong opinions are more likely to participate. These are those surveys where people volunteer themselves to be in them, the self-volunteering ones. The voluntary response surveys, those are highly unreliable because only people with strong opinions usually take the time to do them. Okay, I think there may be 10 questions from each chapter, so that might be the end of chapter 1 right there. Now chapter 2, let's see if I'm right. Oh no, we're still in chapter 1 here. Okay, so it'll be, I guess, not exactly 10, but somewhere close to 10. A customer satisfaction survey for a new coffee shop included this question: given our friendly staff and high quality coffee, how satisfied are you with the experience? See, this is biased right here. They're putting an opinion in here to try to influence your response. Friendly staff, you should leave it up to me to decide if they were friendly. High quality coffee, that's very biased to try to say this. And that this is a leading question, so you don't want to have people have to say, oh yeah, I guess you're right. Just say, ask them what their opinion is. Don't mention this at all. Just how satisfied. You could just delete this whole sentence and it would be better. But this is definitely a leading question because they put things that made them sound maybe better than they actually are in there. And leave it up to the customer to tell you how good or bad you are, if you really want an honest opinion. In a study about dietary habits in the general population, researchers only survey members of local gyms. See, that's bad too. You don't want a sample that's biased towards one group of people. People at local gyms are probably more healthier than people who are not. And they may be on diets more likely that are some kind of healthier eating than people in general. So if you have a very limited sample of who's in there, you're not able to make conclusions about the general population. You want your sample to mirror the population as much as possible. So if half of the population is male and female, then half of your sample should be male and female. If half of the population is unhealthy, then you better put half of your sample to be unhealthy too. They want to talk about the whole population, and in the whole population, some people are healthy, some people are not. But then here, it's almost everybody's healthy, so that's a completely biased survey. This is definitely sampling bias. I think maybe I didn't mention it in this class, but one example that's another example like this is where you want to know the average height of a high school student, and you randomly pick a room in the high school thinking, oh, I'm going to pick a random room, and then I'm not influencing who's in my sample. But what if you end up with the basketball team? They have a class sometimes, and then you might get their room. Basketball players tend to be taller, so now you got a biased sample, and you weren't even trying to be biased. You just want to make sure your sample mirrors the population as much as possible. If you ever take surveys, when they say, okay, what's your age, what's your income, they always ask those initial questions first. What's your race, what's your religion? They're doing that to try to make sure that their sample has equal representation of every group. They're not just trying to be nosy. Select the appropriate word or phrase. Okay, a blank is a bar graph. Okay, we must be in chapter 2 now if we're talking about bar graphs. Blank is a bar graph in which the bars are ordered by size. That's those Pareto charts. Pareto charts come in order. Pareto charts go from highest down to lowest. That's a special type of bar graph. Okay, definitely chapter 2 now. Okay, the following bar graphs, see, these are not in order, so this is a general bar graph when you're just putting them in any order. represents the amount spent by a large country in millions of dollars in different types of environmental conservation, okay? For which type of environmental conservation was the least money spent? So one thing about learning charts and graphs in chapter 2 is to be able to draw conclusions like this. Which type of environmental conservation was the least money spent? It's the bar with the shortest one. So water conservation efforts is the one with the least. True or false? The country spent more on water conservation efforts than on wildlife. That has to be false because we already said water was the lowest one. So how could they spend more on that? But wildlife was actually the second highest one, and water was the lowest one, so that's definitely false. Now, if they would have said it the other way around, that they spent more on wildlife than on water conservation, then it would have been true. Okay, here's one of these pie graphs. Did they do this part for us? Yeah, it looks like it good. Because when we have to fill this in ourselves, it often gets messy to work with. Construct a relative frequency bar graph. Okay, so the first one on here is, I can't even see it because this is in the way there. Watching movies and TV. That was 13.4%. So do they tell me a sample size? No. So I guess we just put that in, 13.4%. Whenever it's a percent, you might wonder if it's that you have to like multiply by a total to get it to be a actual number instead of a percentage. Okay, yeah, something is weird going on here again. Percentage of time spent on these activities, 13.4. I remember this problem in the homework, and there was something weird going on with it, and I couldn't remember what it was. Let me see what they're doing here. 0.13. Okay, so yeah, they're just literally changing it to a decimal. Okay, so let me just get this wrong and start again. There, try another. Okay, so they just wanted you to take this decimal, move it over, change it from a percent to a decimal, basically. So birds are first, and that's 14.7%, so you got to move it over and make it 0.147 and round to 2 decimals, so that's why it'll actually be 0.15. And then dogs are, if you move it over twice, it'll be 256, so that'll round to 26, 0.26. 293 would be 0.29. And fish are 30.4%, so if you move that over, it'll be 0.304, which is 0.30. So this is actually turned out to be a reverse Pareto chart because Pareto charts go from highest to lowest. This one's going from lowest to highest. Okay, which category is the most owned type of pet? It's fish in this example. True or false? More than twice as many households own fish compared to dogs. No, because dogs are 26% and fish are 30%, and 26 times 2 is 52, so it's not even close to double. And notice they correctly started at 0 here too. So that's why a bar of 30 doesn't appear to be that much higher than a 29 would, or even a 26. But if you didn't start at 0, this 30 might look a lot bigger than the 26, and you might think it's actually twice as much. But because this chart was drawn properly, that's false. It's not twice as much. And it doesn't even look like it's twice as, this bar doesn't look twice as tall as that one, anywhere close to it. Greater than 1 in 5 households own birds. 1 in 5 is 0.20. That is true because it was birds? Oh, birds. Okay, no, that's not true. I thought they were still talking about fish. So 1 in 5 is 0.20, and this is not greater than 0.20. So that's false. Okay, that one's correct now. A histogram is skewed to the blank if its left tail is longer than its right tail. See, that's exactly what skewness is about. If you have a high bar near the left side, either at or near the left side, it can be the far left or there can still be some more bars after that. But then there's at least 2 more bars one way than the other. So here's one where I put the highest bar on the left. The left tail has 2 bars, the right tail has 4. That's skewed right. Skewness is based on the longer tail. So it's not where the highest bar is, it's which one has a longer tail. Skewed left has a longer tail to the left and a shorter tail to the right. Skewed to the blank if it's left, if the left tail is longer, that's skewed to the left. So that's what they drew one here, and see here the highest bar is at the far right and there's nothing after that. It can be the far right or the far left. Or there can be some bars on that side too. But literally the highest one is the one on the far right, and there's nothing to the right of that. But there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 bars to the left of the highest one. Nothing to the right. That's highly skewed to the left. Skewed to the left. If I try another, does it give me a different shape? Yeah, see now I'm skewed to the right on this one. So some of these, it's kind of good to try it more than once to see if you get a different example. Sometimes you do it over and over again. It's stratified, 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 and it's like, well, that's kind of a waste of time to keep doing that. Here's one that may be approximately symmetric because the highest bar is at 9, and there's 1, 2, 3, 4, 5, 6 to the right of that. 1, 2, 3, 4, 5, 6, 7, only 7 to the left. It needs to be 2 or more one way than the other to say skewed. And this is, it's not, it doesn't have to be 6 and 6. 7 and 6 is okay to say approximately symmetric. And it's also bell-shaped because it has its highest point in the middle and there's one high point and it tails off on each side. So it's also bell-shaped. Uniform is when it's roughly the same all the way across, and it's definitely not that. But a uniform graph is also symmetric. So if you say symmetric or approximately symmetric, it may be that it's symmetric because it's bell-shaped or symmetric because it's uniform. Unimodal or bimodal, see, bell shapes are unimodal. They just come up to a high point and go back down again. But this one goes up and back down, and then up and then back down. That's bimodal. 2 distinct high points. Even if the first high point is much lower than the second one. Well, I guess they're not counting that then. Maybe you need, I think you need more than one. Maybe that's what's wrong with this, is that there needs to be more than one bar for that to be true, or maybe this just isn't high enough. Let's try another one. See, this is okay. So I guess the problem with that other one is, I think it was 2 things. One is that if one high point is much, much higher than another, then that's not considered another high point, unfortunately. But see, this one's clear because it reaches a high point and then it goes down at least with 2 bars. Apparently you need at least 2 bars, not just 1. And then it goes back up, and it doesn't, I don't think it has to be exactly the same height the second time, but it needs to be close. That other one, I guess, was just not close enough. This one's clearly bimodal. And if I try another, see this here, so it kind of comes up here, but that's so much lower than this one that I don't think they count that, even though there are 2 bars here. This is just too low. So I think it's more about the height than how many bars are in between, but this is not high enough to count as a dip, I guess. Since this is significantly higher than these other 2 peaks, they count that as unimodal then. So it's more about the height. If you go up and back down again, but you don't do it very high, then it basically doesn't count. Okay, stem leaf plot. Okay, here's 5.12, but they already have the 5.1 right here. So you put the 2 in the other box. 4.93, 4.93. 5.00, 5.00. 4.83, 5.23. So this 23 is actually 5 point, oh, I put in the wrong box, sorry. 5.23. Here's another one, 5.18. So I got to put the 8 from the 5.1. This is 5.12, and then there's another number, 5.18. Each of these is a different number. 4.94, 501, 481. So when you get the 1, don't put it like that. I think they'll count that wrong if it's backwards. You need to have it in order, I believe. And maybe we can try it and see if they'll take it out of order, but it doesn't say they have to be in order, but I've seen these counted wrong in the past if they're not in order. 5.09, 497, 502, so I'm going to squeeze the 2 in right after the 1 to keep it in order. 526, 526, 512, so that 2 can go in between or in the front. Either that doesn't matter if they're both 2s. 487, 529, 516, I got to put the 6 between the 2 and the 8. 504, put the 4 between the 2 and the 9. That's the second row. Last row, 4.85, put that between the 3 and the 7. 525, 484, squeeze it in between the 3 and the 5. 515, 524, 503, 519, and 521. I'm going to intentionally put the last one out of order and see if that matters, because it doesn't say here and I'm not sure. Yeah, see, they like that in order. So I got to squeeze that way in the front. See there, I put it in the front now. So yeah, put them in order. I thought so, but it didn't say, so I wasn't sure. And sometimes they're a little more lenient, but okay. So at least see, that's how you get me to do it once, and then if I mess it up, then at least you'll know what to do when you're doing it. Hot coffee. The table provides recorded temperatures in Fahrenheit of beverages served throughout the day. Okay, so there's all the temperatures. Dot plot. So click the pencil. Each time there's a number, just click that. 84 is right there. 89, at least they show you what number you're at right above it. 78, 95, 83, 85, 72, 80, 77, 74, 94, 70, and 90. That was the first row right there. All the way I went straight across like that. So now I'm here at this 87, 291. So anytime there's a repeat, you just hit it twice and they stack up like pancakes. And that could be your highest bar where the shape is going to be determined from. 77, 87. Now we're starting to get some repeats. 85, 90, 72, 91, 83, 70, and 91. See, the highest one is 91. These are like bars of a histogram too. So this is your highest bar at 91. There's only 1, 2, 3, 4 to the right of that. And you do count these blanks that are in the middle. 1, 2, 3, 4 to the right of the highest. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's significantly longer to the left. This would be skewed to the left for sure. I don't think they're going to ask for that, but that if you did ask for the shape, that's what it would be. Are there any gaps? Remember the one we did in the homework didn't have any gaps, but there's gaps here. There's no 71 or 73 or 75 or 76. These empty spaces are called gaps. So yes, this one has gaps. And that's not always easy to tell from the raw data either. The raw data wouldn't show you that. It wouldn't tell you where the highest one is. It wouldn't tell you the shape. That's what chapter 2 does, is it lets you see conclusions real quickly that you wouldn't be able to tell from the raw data. Okay, time series. Notice that there's an even intervals of time here. Every year they take a measurement. The year 2000 had 6.6. Then 6.0 and 5.5. And you just connect the dots. You just mark the spot and connect the dots. 5.0 and 4.7. 4 and 4.9. 5, 8, and 6, 7. 7, 8, 8, 8. 7.3 is the last one of the first row. So here, 5, 6, and 6, 4. I'm just hitting the tab button and it moves me to the next box. 7.5 and 8.2. 9 and 9.6. 8, 5, and 7, 8. 6, 5, and 7, 1. 8, 4, 9, 1. Now this seems kind of made up because it's a little too kind of perfectly going up and down and up and down and up and down like a mountain almost. It's usually not this obvious that there's these nice patterns to it, but they probably just made up the data. So this, it decreases first, then it increases, decrease, increase, decrease, increase. Usually if you collect your own data, it wouldn't be come out this nicely, but they're just doing this for a way to grade you on a problem. So we're still in chapter 2 because that's another chart. A plot that represents how much something there is may be misleading. Oh yeah, remember this? I already mentioned this in the review today. If you don't start your baseline at 0, then that can be misleading. Some graphs it's okay not to start at 0, but a lot of them they need to start at 0, or you can have a distortion and it won't look like something's twice as big, or it'll make it seem like it's twice as big even when it isn't. That was the end of chapter 2, these misleading graphs right here. Here's another one. The other thing you don't want to do is use like area. When you show something's getting bigger by area, that's misleading because now you're making the length twice as big and the width twice as big. So then the area is 4 times as big actually. And if this is done properly, if they're starting at 0, this bar seems to be a lot shorter than that one. So this is like 2.5 times taller, but that's a fair comparison if you start at 0. If this didn't start at 0, these might not be 2.5 times as tall as each other. Graph A exaggerates the increase. Whoops, graph A, I said the right one, but clicked the wrong, they had this out of order. Or no, okay. Yeah, see, graph B is an accurate picture, but graph A exaggerates it. That's these last 2 problems here. They're at the very end of chapter 2. There's a section about misleading graphs. And I told you how there was a book written called How to Lie with Statistics, where they do intentional things like this to mislead people, get a certain point of view across. Okay, the graph is misleading because it's not starting at 0. So this purple one right here, look, this blue bar right here, it seems like it's like 5, 6 times taller than the red one, but it's not even twice as tall. 19,000 is not twice as much as 12,500. It's not even twice as much, but it seems like it's 5 times bigger because you're not starting at 0. So this graph is misleading because it doesn't start at 0. The baseline is not at 0. Okay, now we're in chapter 3, because chapter 3, the first thing we did there is mean, median, and mode. And the median is the best measure of center or central tendency or average because it's not affected much by outliers. I said it, here it is, median. I couldn't find it for a second. The median is resistant because it's not affected by the extreme values that might be outliers. The median is just the one or two numbers sitting in the middle when they're in order. So if you want to make the extremes, the high and the low, very large or very small, the median doesn't care. It's still sitting in the middle. Okay, here's a data set. We're going to find mean, median, and mode. So mean's easy. Add them up and divide by how many there are. 94 plus 85 plus 94, 25, 48, and 83, and there's 1, 2, 3, 4, 5, 6 numbers. So the sample size is 6, n would equal 6. The mean gets divided by n, the sample size, 71.5. And you have to answer all these before you check any of them. Well, there's two 94s. I didn't even put the numbers in order yet, and there's two 94s. And every other number happens once, so 94 is definitely the mode. And this is small enough that I probably wouldn't take the time to write them in order, but it doesn't hurt if you want to. But the smallest number is 25, eliminate that. One of the biggest numbers is 94, eliminate that. Now eliminate the next smallest number, which is 48, and the next biggest, another 94. There's two numbers left in the middle, 83 and 85. So if there was one in the middle, that would be the median. If there's two in the middle, you add them up and divide by 2. The median always comes down to one or the other of those two methods. It's either an odd amount of numbers and there's one exactly in the middle, or there's an even amount of numbers and you take the two in the middle and average them, but not the two that are written in the middle. Notice I'm not doing the average of 94 and 25 just because they're sitting in the middle. You have to put them in order first, or do what I did and eliminate high and low and keep doing till you get to the middle. So the median's 84. The average is in the mean is in the 70s, the median's in the 80s, and the mode's in the 90s. Sometimes they're all different from each other like that. But other times they're all equal too, or very close to each other. Same kind of problem here. And we're doing this from a stem leaf plot. So hopefully you can read this chart and realize, oh, that's the number 9. This is 15 and 19. 26, 27, 28, 28, and 31. And if you count the leaf, there's 1, 2, 3, 4, 5, 6, 7, 8 numbers total. So add them up and divide by 8. 9 plus 15, 15, 19, 26, 27, and a couple of 28s. We got to count both of them. In fact, 28 is going to be the mode because that's the only number that's repeating. And 31. Divide by 8. And round to 1 decimal, so 22.9. Bump this 8 up to a 9 because there's a 5 or higher after it. 22.9. The mode's definitely 28. And they're in order, so eliminate the lowest number 9, eliminate the highest 31. Now eliminate the next lowest 15 and the next highest 28. The next lowest is 19, and then there's another 28 to eliminate. So there's two numbers sitting in the middle when they're in order, 26 and 27. Average 26 and 27. 26.5. Okay, so you can't see the top too well, but everything is green up there, and there's only 3 problems left. So let me, before I forget about it, do the magic word of the video. I didn't write them down, so I'm trying to remember which ones I said already. I know 3 of them for sure, and I think I remember the 4th one, so hopefully I'm not telling you the same one twice. But let's go with this one, the magic word of this 5th video, and this is the last one that counts for your first grade of these. If you send all 5 of them to me, and if I am repeating one, just send it twice, but I think I didn't say this one yet. So let's do the 5th one, will be San Antonio. So send me all 5 magic words, and then you'll get 100 in your O2 4.2 grade for the first video watching assignment. Plus, if you watched all these videos, it should help you do better on homework and the tests. Okay, if all the values in a data set are the same, the sample variance is equal to 0. If all the data is the same, there's literally no spread from them. They're all spread out they're all spread out nothing, literally. So the variance would actually equal 0 exactly if every number was the same. Because then every number minus the mean would be 0, and then you'd have all zeros to work with. But you remember when we actually calculate variance, how that first column where we do all the subtractions, that adds up to 0. And that's the part that doesn't make sense, because unless all the numbers are the same, that's the only time the answer should be 0. Okay, let's do sample variance and sample standard deviation. And oh no, wait, 1, 2, 3. Yeah, this is the bad one where they're giving me 6 numbers, unfortunately. Okay, so 29. Unfortunately, I have a sample of 6, so when I divide by 6, it's probably going to be a messy decimal. But first step in variance is to find the mean. Add all the numbers together and divide by 6. 17 plus 31 plus 25 plus 15 plus 13 plus 16. The sum is 117 divided by 6. We might get lucky here. That might come out better than usual. Okay, that's a lot better than before. At least it's not like 19.83333. That's where it really gets messy. So don't round this. This is nice to work with. Integer would have been better, but at least it's a 0.5 number. So x minus the mean. Whoops. Take each given number and minus the mean that you just calculated. And while you're at it, if you want to do step 3 at the same time, I like to do that. Each number minus the mean, and then you square them all. We square them because if we don't square them, they're going to add up to 0. So the first number was 17. 17 minus 19.5 is negative 2.5. 17 minus 19.5 is negative 2.5, and then if I square it right away, now it's positive. That's the whole point of squaring, is to turn it positive. 6.25. Okay, next number is 31. 31 minus 19.5 is 12.5, or is it? No, it's 11.5. Double check it here and don't take a chance you think you know it like I was doing. 11.5, square that, 132.25. Don't round anything here. If the decimals aren't too long, I would use the whole thing. If you do get the messy decimal one that I had in the homework, then round to 4 decimals if it's really long. But if it's 1 or 2 or 3 decimals, I would use the whole thing. Okay, so then the third number is 25. 25 minus 19.5 is 5.5. 25 minus 19.5. 5.5 squared is 30.25. Three more to go. 15, 13, and 16. 15, 13, 16. 15, 13, 16. They're each going to get minus 19.5. So 15 minus 19.5 is negative 4.5 squared 20.25. So negative 4.5 squared. 13 minus 19.5. Negative 6.5. Should be 42.25. 42.25. 16 minus 19.5 is negative 3.5. Three times 4 is 12, so this should be 12.25. Now, if you were to add up these two positive numbers right here, 11 plus 5, 16, and then you have 2 halves, so that adds up to 17. The positive numbers in this first column, which is step 2, the positive numbers add up to 17. If you add up the negatives, they're going to add up to negative 17, because 6 and 4 is 10, 13, 14, 15, 16, 17. The positives are positive 17, the negatives are negative 17. That column always adds up to 0 no matter what. It's a good double check to add this up and make sure it adds up to 0. But see, that doesn't make sense because you should only get 0 for a variance if every number is the same. That's what the previous problem was even asking about. And it's just due to the fact how means balance positive and negatives from each other. So this is why variance you have to square all the numbers in variance. Otherwise, they'll always add up to 0. But once you square them, anything squared is positive. So if I add up 6.25 and 132.25 and 30.25 and 20.25 and 42.25, and I don't think you can see that, but let me just type them all. 12.25, there they are. So I was just typing them all so I could see them at the same time. The sum of all the squares will never be 0 because if you add all positives, it has to be positive. 243.5. So step 4 is the sum of the squares. 243.5. So the final step for variance is to divide either by 6 or 5. If you're doing sample variance, you divide by 5. If you do population variance, you divide by 6. And I wasn't paying attention in that homework problem, and they switched to population on like the third one, just to show you that does make a difference. So this one, definitely I paid attention this time, and it said sample variance. So then we have to divide by 5. Divide this by 5, and that's the sample variance, 48.7. And then the standard deviation is in essence the 6th step of the process. Once you have variance, if you square root the variance, that's the standard deviation. And round to 2 decimals, 6.97, but there's an 8 after that, so 6.98. So I had to divide by 5 And that's the answer to variance. 48.7. It was exactly 48.7. And then in essence, standard deviation is the sixth step of the process, because you can't even get the standard deviation until you get the variance first. It's always the square root of the variance. So if you square root 48.7, and I'm going to run out of room to write this here, but 6.98. I got it in there, okay. 6.98. So 29's, that's probably the best example of chapter 3. Okay, the last thing is if you know that your graph is approximately bell-shaped, and they literally have to tell you that, that's the empirical rule. So remember we did empirical rule and Chebyshev's. Well, the test only has the empirical rule, it doesn't have Chebyshev's. So just make sure you know empirical rule, it has to be bell-shaped, and the one on the test will be. So once they say bell-shaped, you know it's empirical rule. The empirical rule, there's 3 percentages to memorize. If you're 1, 2, or 3 standard deviations away from the mean, these happen 68, 95, 99.7% of the time. So make a number line, put the mean in the middle. The mean is when you're 0 away from the mean, so that's just a z-score of 0. They tell you the mean here is the average weekly expenditure on coffee was $44.23. And then the standard deviation was $3.03. It's a little off the screen, but right there at the very end, 303. Whoops. 303. So add that 3 times and subtract that 3 times. 44.23 plus 303 is 47.26. That's the positive 1 level. Add 303 again. 50.29. This is positive 2. Add 303 again. 53.32. Positive 3. So go back to the mean, 44.23, and subtract 303 3 times. 41.2, or what could be 41.20 if I write them all with 2 decimals, minus 303, 38.17, minus 303, 35.14. But see, I do this before I even read what the question's asking for, because I don't want to get influenced by numbers that I see down there. But I have every possible number they could ask for. And they're only going to ask for the 1 and the negative 1 together, or the 2 and the negative 2, or the 3 and the negative 3. It would never be negative 2 with positive 3, or positive 1 with negative 3. You can't do that if the numbers are uneven. Not till chapter 7 anyway. So just make sure it says between. I think all their examples are betweens, because I use another book at HCC and they sometimes ask for above or below, but this I think is always between, which is the easiest case. Estimate the percentage of weekly expenditures that are between 35.14. Where's 35.14? So now I don't have to scramble to figure out where that is. I can just look on my number line. That's negative 3. So the other number better be positive 3. 53.32. Yeah, see, that's the positive 3 level. So the answer is right here, 99.7. And they don't put that for some reason. It just says almost all, but It's technically 99.7. I don't know why they don't put that on there, but it's almost 100%, but it's actually not quite 100%. What about if you're between 4120? 4120 was the -1 level. And 4726 is the positive one, see? So by making the number line first, every answer you need is here somewhere. You don't have to recalculate every time there's a new part. So 1 is 68. And that one is in the chart here, see 68. And then you can do the backwards version where it says between what two values are 95%. Well, 95 is the other memorized number. The first two, I was going like this to get the percentage. Now I'm given the percentage and I want to know how many places out. That's 2 places out. So one answer is this 3817. And the other one's this 5029. And always put the smaller number first. 3817. And the other green one was 5029. That's the empirical rule. And it goes both ways. They can give you the 2 scores and ask for the percentage, or they can give you the percentage and ask for the 2 scores. And luckily, all of yours are always about between, so you don't even get the hard case that can happen sometimes. Okay, we did all 30. Everything up here is green. And I did have a couple of weird cases, unfortunately, in Chapter 1. Sometimes you get an easy case and then another version is a harder case, so that's just the luck of the draw. We can't control that, but that's everything in this review video. And now you've seen everything you need to know for the first test, multiple times even, especially with the review as a second time around. And now you just want to do the homework and the review as much as possible before taking your test. Luckily, there's a 2-day window for the test, so most people will review the first day, and there's actually a review day on Thursday, and then you can still review on Monday, and then take the test Tuesday. Some people take the test right away on Monday when it first opens up, but there's only one attempt, so if you take it right away and do bad, then you don't get to retake it, unfortunately. So most people study as much as possible. In fact, a lot of them aren't even near close to where they should be on the calendar. So they're actually scrambling to finish homework on Monday and Tuesday, and they don't even get it all done, and then they end up with a bad test grade when that happens. But if you kept up with the suggested calendar and finished all the homework and you're just reviewing now and studying, that's your best chance to get a high grade on the test. So this is the end of Unit 1, Chapters 1 through 3, and then after we take our test, we'll be moving on to Unit 2, which mostly covers Chapters 4, 5, and 6.